We are on Unit 7. This is the fourth lesson of Unit 7, so Notes 4. Today we are continuing doing volumes of solids of revolution, just like last time, but this time we're using a different method to find the volume, and this is called the cylindrical shell method. If you remember last time we did the disc and washer method, where we just found cross sections that were circles. And so it was another take on the cross sections that we did in Notes 2, but that time they were all circles. Okay, so this time we're doing the cylindrical shell method. So let me introduce this to you, and let me introduce why we would even do this. So I'm going to draw a curve, and so I'm going to say this is the y-axis and this is the x-axis. All right. And this curve, I'm going to sketch out a region, and it's going to be a little goofy, and I'm doing this kind of to make a point. So let's say that this is f of x, and it can continue, whatever, it can continue, but our region is going to be contained in that. And then g of x is going to look something like this. Something like that, okay? So, and then that would continue as well. So these would go like that. But this is g of x, okay? All right. If we were revolving this region around the x-axis, we would do discs, we would do cross sections that were circles. So we would do the washer method, okay? Just like we did last time. Let's revolve this around the y-axis. Let's take this around the y-axis. So if we did that, what we did last time, we made a dotted line on our axis of revolution, okay, and this, if we revolve it around the y-axis, the sketch on the other side would look something along these lines. Something like that, right? And then we would revolve it around, so it would be a solid. Right? Be kind of a cool looking solid. The problem though is if we did the disc and washer method, we would be making a line from the axis of revolution to the far side of the region. That would be our big R. The problem is if we drew the line here, big R would be g minus 0. If we drew the line here, we run into a big problem because this is f of x, but then we would need, it would get very complicated. Don't you agree? It would get very complicated. It's like, do we draw big R here? Do we draw big R to here? What's going on there? It gets really complicated, and the disc method just is not very, it gets cumbersome to use. Maybe it wouldn't be impossible to use, but we would be subtracting things, and it would be quite a mess. Okay, this is a good example of when the cylindrical shell method is more useful. So here's what the cylindrical shell method is. I'm going to draw a slice, but instead of drawing it from the axis of revolution to the far side of the region, I'm going to draw a slice in the x direction, have a little delta x. So I'm going to draw a slice. I'm going to make that slice maybe just a representative slice. So that's my little slice, okay? So eventually we're going to give it a little thickness. So that little thickness of that slice will be a little delta x, right? So even though we have this vertical axis of revolution, we're going to have a delta x in our problem, so we're going to have a dx in our integral, okay? Now, this slice, I'm going to revolve this around the y-axis like that. So when I revolve this around the y-axis, its reflection will be, I don't know, somewhere maybe over here. Something, that's not right, but you get the idea. It's somewhere around there. And then when we revolve it, do you see that it forms a cylinder? When you revolve just this one little slice, we get the exterior, the curved area, the curved region of a cylinder. Do you guys see that? Okay. The radius of the cylinder is going to be here. The height of the cylinder is going to be here. Okay? This whole thing here. All right? And then we are going to give it a little thickness. It's going to have a little delta X thickness. All right? So we need to think about, what I would like to think about is, what would the area of just that cylinder, that part of the cylinder be? The area of a cylinder, in fact, not the whole cylinder, just the area of the curved surface of the cylinder. What is that? Well, if we take this surface apart and lay it out flat, it's going to be a rectangle, isn't it? And the length of the rectangle will be the circumference of that circle. And the height of the rectangle will be our h. So the area will be the circumference of the circle, 2 pi r, times the height, right? So that will be the area of just the cylinder, okay? If we want to find the volume, if we give it a little thickness, then it has volume, right? And the volume of that one cylinder would be 2 pi RH times delta X, right? So that would be the volume of one cylinder. And if we start with the innermost cylinder, if we start with, well, the innermost, I don't know why I stopped there. If we start with the innermost cylinder and then go out and then keep going out, then do you agree we would get the entire volume, the entire volume of the solid? So what we want to do is take this one, cylinder. We want to add up all the cylinders from the first one to the nth one, right? And then we want to let the number of cylinders go to infinity, right? This will give us the integral from where to where? From, in this case, it was going from 0 to whatever this x value was, right? 0 to whatever that x value was. In general, though, we could have started this out here at some other x equals a. So let's just call this x equals a here. So this is going from a to b of 2 pi RH dx. 2 pi RH dx. Remember, h is this distance. So that's just the top minus bottom. Those will likely be functions. They can be functions, so there might be x's in there. R, what was R here? So R here will change with each cylinder, right? The first R is very small, the next R goes to here, the next R goes to there, the next R goes to here. So R changes with each cylinder. So R is not a constant here, it changes. And from the y-axis out, that will just be whatever value of x we're on, right? So in this case, R is equal to x. It will not always be equal to x, but in this case it is equal to x. Okay? So, our formula, go to your notes sheets now, our formula that you can put at the top of your sheet here is volume is equal to integral a to b of 2 pi RH dx. You of course can do this with a dy as well. It's just the most useful, the most times that we'll use this are just when it's a dx. I don't know that I ever will give you one where it's where you would need a dy. Okay? But you certainly could. You certainly could. All right. Let's look at some examples. Find the volume of the solid formed by revolving the region enclosing y is equal to 2x, y is equal to 0, that's the x-axis, and x equals 3, that's the vertical line at x equals 3, about different axes, okay? All right, so this is just a line through the origin of slope 2. And we want to end at x equals 3, and one of the boundaries is the x-axis. So this is one where we're just looking at the first quadrant for this. So y is equal to 2x, y is equal to 0, x is equal to 3, right? When x is 3, what is this y value? That'll just be a 6, right? So this is 6 right here. Okay. So we want to first revolve this around the y-axis. This is one where we certainly could just use disc and washers. It would not be hard at all to use disc and washers. Do your big R, do your little r, you're good to go. But for the sake of teaching you the cylindrical shell method, I want to do this by cylindrical shells. Okay, so think about this. Think about, where's my pencil? Here's our initial region. Let me give that a little shading just for this first problem. Okay, and then we're going to revolve this around the y-axis, so it's going to be like flipped over here to the other side. And here's what this looks like in general, right? So the inside is open and the solid is only on the outside, right? Okay, draw your slice and if you're doing the cylindrical shell method, you make your slice parallel to your axis of revolution. You don't touch your axis of revolution, you make it parallel to it, okay? Only through your region. And now revolve that slice as you would with the entire region. Revolve that slice. And you'll see your cylinder, okay? It's going to have a thickness of a delta x, so this will be a dx, okay? Here's the height. So the height is top minus bottom. So this is 2x minus 0. So the height is 2x. Okay. Where's your radius? Well, your radius always goes from your axis of revolution to your slice. Okay. So in this case, what is that? Well, that will change as we go. It's not a constant, because as we make different cylinders, that will change. So this is your x. From the y-axis to your slice will be the x value. Okay? So r here is just x. So the volume expression will be the integral from, okay, we're doing a dx, so look at your region, and give me the x extremes of your region. So the x started at 0 and it went to 3, so we need to go from 0 to 3. Do not go from -3 to 3. Only use your region there, okay? And then our formula for a cylinder, area of a cylinder, 2 pi RH delta x, right? So 2 pi, r is x, h is 2x, so times x times 2x, I'm going to squeeze it in, dx, okay? Let's go to your calculator. Math 9, 0 to 3, 2 pi times x times 2x. dx. 113.097. If you wanted to find out what that was without pi in there, then just divide out pi. So this would be 36 pi. Back when we did here it was yesterday when we did the disc and washer method, we did this exact same problem using, it's hard to see here, I wish I had saved my other colored one, but we did the same problem using disc and washers in this case, okay? And look, we got the same answer, doing it a completely different way, okay? Let's take a look at another. Same region. This time we are revolving it around x equals 3. That's over here, right? So when I draw it, I'm going to draw it way over here. Okay, there's my region. Here's my axis of revolution. Okay? So we're going to draw a slice. This time I'm not going to draw the whole solid. I'm just going to draw my slice. There's my slice. And I'm going to revolve that one slice so that I like to see my cylinder in here. So view your cylinder. It will help you, okay? Here's the height of your cylinder. So the height is still top minus bottom, so that's just our 2x minus 0. Now where's your radius? Well, the radius is right here, isn't it? The radius is right here. Remember that from the y-axis to your slice, that is x. That is always x. So what expression can we say r is? Well, if the whole thing is 3, we need to take away x, right? So r will be 3 minus x. So this volume will be the integral from 0 to 3 of 2 pi r h dx. And when we put that into our calculator, we get 56.549, which is 18 pi. Okay? Next one. We're going to now revolve it around the line x equals 4. So x equals 4 will be out here. So let's see what that does. Here's our region. And now we're going to revolve it around x equals 4. So dotted line, always on your axis of revolution. Dotted line there. Now draw your slice. Here's my slice. It's going to be parallel this time to the axis of revolution. And now make your cylinder around your axis of revolution. Here's the height. There's the height. The height is still 2x. Height is still 2x. Okay? What is the radius this time? Well, I can see the radius. Here's the radius. There's the radius. From the y-axis to our slice is x. So the radius must be 4 minus x. So 4 minus x. So the volume will be the integral from 0 to 3, 2 pi r h. And when that goes into your calculator, we get 113.097 again, which is still 36 pi. Okay, let's take a look at another one. Oops. Am I still going? Yeah, I just lost power here. Let me plug in. Sorry. Okay. Let's take a look at another example. Find the volume if of, that should be an of the region enclosing y equals x squared. That's just our parabola, right? Y equals 0, that's the x-axis, and x equals 4 is out here. So the region's going to be this piece right here. Okay? We're going to begin by rotating it around the y-axis, so let's draw our region. It'll be this piece of a parabola, and then this is at x equals 4 here. Okay? All right. Y-axis. So draw a dotted line, dashed line on the y-axis, and now make a slice parallel to your y-axis inside your region. Make your cylinder. Making the cylinder allows you to, okay, this red is going too. What's going on here with my reds? Okay. This just allows you, it really helps you to see the radius. I find kids have a hard time seeing the radius sometimes. They can totally see the height. Sometimes they have a hard time seeing the radius. So draw your cylinder and that'll let you see the radius. The height is top minus bottom of your region. So x squared minus 0. The radius is always from the y-axis, well, from the axis of revolution to your slice, wherever that is. It's always from your axis of revolution to your slice. That's your radius. So in this case, that is x, right? Because the axis of revolution is the y-axis. So our volume will be the integral from 0 to 4. Again, remember, only do the x values of your region here, okay? And then 2 pi r h dx. When we put that into our calculator, we get 402.124, which is 128 pi. Kind of big. This time we're going to revolve that same region around x equals 4. So we'll draw it. Okay, and here's our axis of revolution. Draw your slice, and then revolve your slice so that you can see your cylinder. Okay, here's our height. Height is still x squared, top minus bottom. Here's our radius. There's our radius. What expression do we need for our radius this time? Well, from the y-axis to our slice is x. So we need 4 minus x, right? 4 minus x. So the volume will be the integral from 0 to 4, 2 pi r h dx. Remember, the dx gives us a little bit of width of that. Otherwise, it's just a line, and a line has no width. So the dx is vital here. Put it in your calculator. We get 134.041, which is 128 pi divided by 3. Let's do it around the line x equals 6. That will be out here, right? So same region, and this time y equals 6 out there. Slice, revolve your slice so that you can see the radius. There's the height. Height is still x squared. Here's our radius. So the radius expression will be 6 minus x to get r. So 6 minus x. Remember, from the y-axis to your slice is always x. Sometimes that's also the radius. But if your axis of revolution is to the right, you're going to need to subtract that x. Integral 0 to 4, 2 pi r h dx. And we get 402.124, which is 128 pi. Okay, next up. Find the volume of I must have copied and pasted that, of the region enclosing y equals x cubed. We know what y equals x cubed looks like, right? X equals 0, that's the y-axis, and y equals 8. Y equals 8 is up here, so the region is going to be right there. So take your time finding that region, otherwise your whole thing is going to be messed up. So when I draw this region, it's going to look something like that. That's the region. We're going to take the region and we're going to revolve it first around the y-axis. So here's our slice. Here's our cylinder. We can see the height. The height is the top minus the bottom. I need to find out what this y-axis, what this y value is here. So we got that by putting, oh, that was just y equals 8. Never mind, we don't need to go find it. It's y equals 8. We were given that, right? We are going to need to find this x value, though. What is that x value? Well, if we put y equals 8 in here, x has to be 2 right there, right? So the height is going to be 8 minus the curve, right? Top minus bottom, so 8 minus x cubed. What is the radius here? Well, here's the radius, which in this case is just x. So the volume is the integral from, these are the extreme x values of your region. So 0 to 2, 0 to 2, 2 pi r h dx, 2 pi r h dx. This turns out to be 60.319, which is 96 pi over 5. This time we're going to revolve that same region around x equals -2, so it'll be over here, okay? So here's our region still. This time we're revolving it around x equals -2. So here's our slice. Revolve it around x equals -2 so that you can see the cylinder. And I know this isn't quite right, but we can see the cylinder. I can see the radius. I can see the height, right? So the height is still 8 minus x cubed. 8 minus x cubed. What is the radius this time? Well, remember that the distance from the y-axis to your slice, this distance is always x. That's always x. So what do we need to do to x to get r? How can we write an expression for r here then? Well, this distance is 2, right? This distance is 2. This distance is x, and r is 2 plus x. So 2 plus x or x plus 2, either one. So our volume will be the integral from 0 to 2 of 2 pi r h dx. 2 pi r h. That turns out to be 211.115, which is 336 pi over 5. We are doing great. Now let's come and take the same region and revolve it around x equals 5. So that's way out here. So I'm going to draw it way here. So here's my region. That's 2, right? So y equals 5, x equals 5, way out here. Okay, 5. Slice, revolve it, okay, so that you can see the radius. It's just helpful to see that radius. Okay, there's your height. Height is still 8 minus x cubed. Okay, what's the radius this time? Well, from your y-axis to your slice is always x. So r will be 5 minus x. 5 minus x. So our volume is integral from 0 to 2 still. Remember, it's only your region. Only your region. 0 to 2, 2 pi r h dx, and that turns out to be 316.673, which is 504 pi over 3. So that is the cylindrical shell method, and I really love it. I love using it instead of, I will use this instead of changing, getting x equals and doing a dy in the disc and washer method. Okay. Sometimes though, this is a really useful method. Sometimes it's just more convenient than the disc and washer method. Now I need to tell you this. This topic, this cylindrical shell method, is one of the topics that is usually in Calculus 2 in college. It's in Calculus 2. But this is not on AP. This is not on AP. So College Board does not have this in their curriculum for this class. This is one that I teach because, number one, it's so easy to do. I know you can understand it. It's the same thing as the disc method. And number two, it does make things more convenient sometimes. So I have students who really do prefer this to the disc and washer method. For me, again, I will try, since now we know the cylindrical shell method, I will pretty much just use dx's all the time, because you almost always, our equations are in x's instead of y's. So this allows me always to use a dx, even though with a disc washer we would need a dy. Okay. Now that you know both methods, you can choose which method to use. Okay. However, if it's the AP exam, and if the question asks you to find the integral that gives the area, not find the area, find the integral that gives the area, know that they're not going to be using the cylindrical shell method. They will be using the disc and washer method. Okay, so just keep that in mind. But if you're just asked to find the area, you can use whichever method that you want to. Even if it's a free response, they will all recognize this. They know what that is. Okay, the people grading the exam know what that is. So you can totally choose which one you want to use. Okay? All right, now it's your turn to go and practice.